We're very excited to have Charles Elkan here. Charles has had a fascinating career. He got his PhD in computer science from Cornell and went to work at UCSD, where he was a tenured professor of computer science in their outstanding department. So from there, he went to Amazon. He was the original Amazon fellow, and he led a team of 30 scientists there to do essentially machine learning projects across the firm, e-commerce, cloud computing, and others. Since then, he's joined Goldman Sachs, where he's a managing director and their global head of machine learning. So we're very excited to hear comments now from Charles.
Thank you, Brian. Thank you. All right, can everyone hear me? So I think my talk is going to be a good complement to the previous talk. It's going to be less specific about machine learning and finance and more general about artificial intelligence. And I'm going to talk some about the history of artificial intelligence and some about what we can expect from the future of artificial intelligence. This is a talk that I've given versions of before, and in fact, the first version was for a Goldman Sachs conference for clients, and I was specifically asked to talk to clients about what's real and what's not so real, because people read a lot in the media about artificial intelligence, and I think some of it is exaggerated, some of it is hype, but then there is a lot of reality. And in the previous talk, we heard about the reality of machine learning and finance, and there really are great opportunities. Let's see, how do I move the slides forward? There. All right. So let me talk a little bit about the history of artificial intelligence. As a research area, it's interesting. It has a well-dated beginning, and that's the year 1956. So electronic computers really became a reality in the 1940s, and actually even in the 1930s, really the founder of the field of computer science was Alan Turing, and he envisaged the use of computers for artificial intelligence and wrote some really thoughtful papers about that, but the computers didn't exist until the 1940s. And so in the 1950s, and specifically in 1956, there was a workshop at Dartmouth College where some of the top leaders in the field came together, actually named the field artificial intelligence. And the gentleman in the photo here is John McCarthy. So he was one of the founders of the field of artificial intelligence, participated in the conference in 1956 at Dartmouth. This photograph is from 1967. And one of the reasons why I put this photograph here is actually, so John McCarthy was my advisor when I was a visiting graduate student at Stanford. So although the field is more than 60 years old, there are still a few of us who have a connection to the beginning of it. And so for those of us who have been working in the area for a long time, it's almost, you could say, amusing that there is so much public attention and so much excitement now when it really isn't a new research area. And interestingly, from an academic point of view, artificial intelligence has been really a respectable area of research in universities, an area of research in which people have been able to get jobs and been able to get tenure for this entire 60 years. But at the same time, it's been an area of research that also has attracted a lot of skepticism from faculty in other departments and from administrators. So we've always had this interesting insider-outsider status. What's I think fascinating also is that really the cliches of the field haven't changed in 60 years. So this picture is from 1967. It's obviously staged, and you can see that one of the things it's supposed to make you think of is big computers and great computational power. It's also supposed to make you think of great human intelligence. Not just some ordinary activity that would require ordinary intelligence, but playing a game. And not just playing any game, but playing a game that is a very intellectual game with world championships. That's the game of chess. And of course, in the recent excitement about artificial intelligence, one of the sources of that excitement has been neural network systems which have defeated the world champion at the game of Go which many people would say is a game that is even more intellectually challenging than chess. Now, people, of course, talk a lot about machine learning nowadays, and sometimes they seem to think that machine learning is synonymous with artificial intelligence. So let me try to talk about what the distinctions are. So there are many subfields of artificial intelligence. I've listed 4 of the important ones here: natural language processing, machine learning, computer vision, automated reasoning. And actually, one of the open questions that's foundational in artificial intelligence research has always been, are some of these subfields actually more fundamental than others? So it might be, for example, that what's really key to human intelligence and therefore to artificial intelligence might be language. After all, humans are the only animals with language. Or it might be key that visual abilities are what's needed for intelligence. You know, octopuses are very intelligent, and pigeons are very intelligent, and they have strong vision also. There's an interesting, somewhat speculative theory in evolutionary psychology, actually, that human language ability in the brain is actually a reuse of modules in the brain that evolved for vision. So perhaps vision is fundamental to intelligence. And there is something of a consensus nowadays that in fact learning is fundamental to intelligence. And the biggest progress in artificial intelligence has come from the development of learning algorithms. And for example, all the most successful computer vision methods nowadays are based on neural networks and are based on learning from very large data sets. But it's the field, we haven't achieved artificial intelligence, so it's still not completely an established fact that machine learning is the most fundamental part of artificial intelligence. There are some important distinctions in practice. So sometimes people talk about artificial general intelligence, and that's the research area which really is aimed at trying to replicate what you might call human-level intelligence, or possibly the robustness of animal intelligence. So artificial general intelligence is really a scientific research field and not aimed at any particular applications. But most of what we do in industry is aimed at applications, and so that's called applied AI often. There's also a lot of excitement nowadays about data science. I think especially in business schools. You know, just Friday last week I gave a talk at the Tepper School at Carnegie Mellon, and I was hearing about how they've just created a new master's program in data science. And my own university, University of California, San Diego, actually has multiple programs in data science. Well, I make a big distinction between data science and automated decision making. And when I was at Amazon, we really placed more value on the automated decision making than we did on the data science. Of course, data science is important, but essentially it's analysis, and maybe it's retrospective explanation. But in business, the word that we use is production. At Amazon, for example, it's interesting to do data science to see which customers are going to be interested in buying shoes, but ultimately that doesn't actually sell shoes. What actually sells shoes is to have real-time recommender systems that when a customer is on the website and they might be interested in shoes, then we show them a recommendation for shoes, and then they actually buy those shoes. And we're in a similar situation at Goldman Sachs. We have flow. We have thousands of trades. Maybe we have millions of bids and quotes. And we need to automate the decision making around that. And so we are hiring at least as many software engineers as we are hiring data scientists, because it's the automated decision making that really creates the business value. All right. So why are people so excited about artificial intelligence nowadays? And they definitely haven't always been excited about it. In fact, when I was an assistant professor and my School of Engineering had a new dean, and he came from a background in nuclear physics. His whole career had been to work on nuclear fusion, which has been a sink for billions of dollars of research funds with so far no return on investment for society. But the new dean comes and assistant professors are meeting the new dean and talking about what their research area, and I used the phrase artificial intelligence, and he frowned. And he really did not think that artificial intelligence was a respectable research area, even though my colleagues in the Department of Computer Science did think that it was a reasonable research area. Well, deep learning is the major reason why people outside computer science are excited about artificial intelligence nowadays. And I would disagree a little bit with the previous speaker. I think there have been some significant research innovations in neural networks. I would call this a Kuhnian wave of scientific progress. I wouldn't call it a paradigm shift. I think we're still in the same paradigm of machine learning and artificial intelligence. But there was a definite combination of research advances and very much advances in computational power that enabled some impressive new applications about 5 years ago. And incidentally, the advances in computer power have not just been in supercomputers and not just been at the largest research institutes like the Berkeley Lab. Almost all the deep learning nowadays is happening using GPU chips, which are on cards, which are mounted in personal computers, which are very accessible. And the accessibility of compute power is really just as important as the magnitude of the compute power. So the progress that deep learning has enabled has been especially in vision and especially in the combination of natural language and vision. So here's an example of the sort of problem that a deep learning system can solve that was unsolvable by any type of system 10 years ago. So here's an image, a sort of random photograph, and a question: how many leftover donuts is the red bicycle holding? And this is actually a training example for the software. So in this training example, we're given the answer. So the answer is 3 in this case. But with enough training examples like this and feed it into a neural network which has the right design, use enough compute power, which actually is the compute power that's available in a single personal computer nowadays, then you can have a software system that can actually answer questions like this. So essentially it can recognize that somewhere in the image there are these things called donuts, and then it can actually recognize that there are 3 of them as opposed to 2 of them or 4 of them. So these applications, it's very easy for people outside the field to understand what they do and to see that indeed it is an impressive achievement. And so that generates excitement, and then people wonder, what can these same techniques do in their own areas of application. And in fact, deep learning does yield higher accuracy in many important application areas. And an example I'm going to talk about now, I'm going to talk about in a minute, is forecasting. But let me first spend a few minutes trying to explain what deep learning really is. So it is the current generation of neural networks. It is nothing more and nothing less. And I was emphasizing that artificial intelligence is not a new research area. Well, neither are neural networks. Neural networks were invented in the 1950s. The name that's usually associated with them is Frank Rosenblatt, who was a professor at Cornell. And there was a wave of excitement around neural networks in the 1950s and then continuing into the 1960s. And then there was really no research progress for more than 10 years. And actually there were some major reports that were commissioned by government agencies in the United Kingdom and the United States, where physicists in particular looked at the state of research on neural networks, artificial intelligence, and said that it was never going to succeed, and so governments should no longer provide research funding for it, and they didn't for a while. But then in the 1980s, there was some great research advances. Interestingly, some of the same scientists who were at the forefront of those research advances in the 1980s were also the same scientists were at the forefront of the advances in the 2010s. So these people continued doing research in the field and with great persistence had success again. And one of the names you may have heard of is Geoffrey Hinton. And again, I was lucky. Jeff Hinton was a postdoc at University of California, San Diego. I didn't actually overlap with him there. I overlapped with him at Toronto. And so in the 2010s, there were some algorithmic advances, really significant, and then modern computational power. And something that people in the field of machine learning, I think, have appreciated for decades, but perhaps some outsiders have not appreciated, is that there's no conflict between machine learning and traditional statistical methods. But there are many types of data for which traditional statistical methods are just too simple. There's no way in which you can understand language, or in which you can understand speech, or in which you can understand images using linear models. So if we're going to have any chance of success at dealing with those types of data, we're going to need complex nonlinear methods, so machine learning methods. And this diagram on the right here is an illustration of a simple, by modern standards, deep learning network for doing computer vision. So the input is an array of pixels, 512 by 512, black and white. So actually this is a very simplified input. If you think of a 4K television nowadays, it's 2000 by 2000. It can be 60 frames per second. It's color. So the amount of input data that we have nowadays is massive, even compared to just simple photographs. And then there are many layers of processing. And actually here where it says L1, 256 by 256, that's essentially a matrix of nodes. And each node is actually a single linear model. So if you compare the complexity of a machine learning model to a linear regression model, just in the bottom L1 we have essentially 65,000 linear models. And so this whole neural network, which is simple by today's standards, is perhaps about 200,000 linear models, and then there are nonlinearities that are combining the linear models. And that essentially is what a neural network is. And then if you look on the right, there are 5 output nodes. So what you finally get out of this neural network is 5 numbers. And the neural network can be trained so that those numbers are essentially predictions or recognition of what it is that you're interested in recognizing. So for example, one of the 5 output nodes might be a yes-no output, so 0 or 1, is there a cow in the picture? And in this particular picture, yeah, there is a cow, and of course cows have many different appearances, many different sizes, and the neural network will be trained to recognize a cow under all its different appearances. So this is what deep learning is. All right, so deep learning is really successful for many applications where traditional methods don't succeed. So this is an application that my team built at Amazon. So Amazon actually sells hundreds of millions of products and has at least tens of millions of products in stock in their warehouses, and has the classic retail management decision of purchasing. Essentially, like any other retailer, Amazon has to place an order and get products in stock, and then once the product is in stock, then Amazon hopes that consumers will come and buy these products. And it's very easy to be overstocked, and that's expensive. It's also very easy to be out of stock, and actually being out of stock is more expensive than being overstocked, because when you're out of stock, then you disappoint the customer, and the customer may not even come back. And then, of course, you've lost the revenue if you're out of stock. And so Amazon needs to forecast tens of millions of time series and needs to update these forecasts on a daily basis or minimally on a weekly basis. And actually, nowadays, because Amazon has so many warehouses and millions of products can be in stock in any given warehouse, and so Amazon needs to forecast the demand that's going to be assigned to each of the different warehouses, because of course Amazon mostly ships with 2-day shipping or even same-day overnight now, and essentially if you buy a $15 item with 2-day shipping and it's in stock in your nearest warehouse, then Amazon can deliver you that item and make a small profit, only a small profit. And if the item is not in stock near you but is in stock across the country, well, Amazon has to bite the bullet and pay for 2-day air shipping, and then Amazon loses money. So forecasting demand is absolutely crucial. And with tens of millions of products, then every day there are thousands of new products. And for almost all these new products, Amazon makes an automated decision about how many to order from the supplier. And of course, for products that are already in stock, then Amazon makes automated decisions about reordering to restock them. And of course, you want the new order to arrive before you run out of the old stock. So at the top here is an illustration of 4 typical time series for products and typical forecasting products. So, So here's the timeline: 2015, 2016, 2017. The black line is the actual demand. The vertical blue line is the time at which we're making a forecast. The jagged blue line is the mean forecast. But in fact, we're not very interested in making a mean forecast. Instead, we want to forecast an interval, say a 90-95% confidence interval. And so that's the shaded blue area. And you can see, for example, that for this product, there was a forecast spike in demand in the holiday season of 2016. And the actual demand was much higher than the forecasted demand. But the actual demand was just within the 95% confidence interval. So from that point of view, we got the forecast right. And this product is interesting because this is a product that was actually brand new in the middle of 2016. And so the point where we made the forecast, we only had a tiny amount of history. But we still needed to make a forecast for a whole year into the future. And even with this tiny amount of history, we were able to predict that there was going to be a seasonal spike in demand here, and that there was also going to be another seasonal spike in demand here. We didn't predict the strange dip in demand here, but we did get the actual demand within the envelope. And so you can ask the question, how is it even possible to predict a time series for a year in the future when you only have maybe 2 weeks of data now? There's none of the standard ARIMA or time series prediction methods can possibly do this. Well, the answer is actually simple at a conceptual level. One is that we share information across many products. Essentially, the products fall into high-level categories, and we have one neural network per category. So this was actually also a big software simplification compared to using ARIMA-type methods, because in ARIMA-type methods, you have a separate model for each time series, and so that's tens of millions of models. But now we only have hundreds of models because we have one neural network per product category. And so in a given product category, there are going to be seasonal patterns which are shared across different items in the same category. And then what we also use as input is we actually use the product descriptions. So if we have a clothing category and we have a product and it includes the keyword bikini in the description, well, bikinis have a certain pattern of seasonality and demand. And if we have a new bikini that comes into stock in May, and then we sell 2 of it in June, well, that's really enough to predict that the demand in July maybe is going to be somewhere between 5 and 20, because just that little bit of information tells us the magnitude of demand, and then we combine that with the seasonality. And the neural network is capable of combining all these different pieces of information into a reasonable forecast. This diagram is a high-level diagram of what the neural network is, and it's actually something which is called a recurrent neural network. So it specifically takes as input a sequence of values, and then the output is also a sequence of values. And one of the important technical pieces of progress in the last few years has been, essentially the algorithm that is used for training neural networks is called backpropagation. It was invented in the 1980s with some antecedents in the 1970s. But backpropagation, nobody knew how to make it work for training neural networks that had long sequential data inputs. And then the actual research breakthrough for training these sequential neural networks was in the late 1990s, but people didn't quite appreciate that research breakthrough until the early 2010s. It was sort of rediscovered and then understood. So now we can indeed train neural networks which take time series as input and produce time series as output. And it's just, there are going to be situations where you have very limited data, where a more traditional linear model will essentially overfit less and give better forecasts. But for complicated situations, then I think the neural networks are the way to go. All right. So what can deep learning not do? I think this is a very important question because if you look at the press, you seem to give the impression you can do everything. And I think the fundamental issue is that AI methods give us shallow understanding, but don't give us what I would call deep understanding. And if you've taken any class in analytic philosophy, you might have heard about, so how do you actually define concepts? Well, what's an operational definition of a concept? So it's almost an algorithmic way of recognizing a concept. So operationally, understanding is the ability to answer questions of many different types correctly. I think that's what you mean when you say that a student understands a concept or doesn't understand a concept. And shallow understanding is the ability to answer a limited range of questions where those questions all fall into the same category. And then deep understanding is multi-layered, it involves context, it uses background knowledge. It's interesting etymologically, if you go back to the root of the word intelligence, to be intelligent is to be able to select the correct answer to a question. Here's an example of what I would call deep understanding. So shallow understanding is the ability to look at the picture, look at the question, answer three. But the first time that I used this picture in a talk, it was when I was asked to give a presentation to the board of directors at Amazon about machine learning. Because not surprisingly, Jeff Bezos knows a lot about machine learning, but the board of directors are mostly significantly older than Jeff and don't have the same background and really don't know much about machine learning. So I was asked to give them a little bit of education. And so I was explaining what deep learning is with this picture. And then Jeff Bezos actually put up his hand and said, hey, the answer is not 3, the answer is 3.5. And he was pointing down here, this looks like it's a half donut. There's 3.5 leftover donuts. So then that makes you think, well, what is the answer? Is the answer 3? Is the answer 3.5? I would argue that the answer actually might be 3 in 2 pieces because here's one piece, here's another piece. So why would you say 3.5? Well, actually, it's because you have this general knowledge of gravitation, which people had even before Newton. And so intuitively, unconsciously, you know that if these were 2 separate pieces of donut, then they would fall down and you wouldn't even be able to see them. So I think this is an example of deep understanding, of being able to explain why the answer is 3.5 and why the answer is not 3 in 2 pieces. And then deep understanding is also being able to explain, well, if the intent of the question is how many people can I feed, the answer is 3 because nobody wants to eat somebody else's half-eaten donut. This is a level of understanding that humans have even before they can read and write. Little children can answer questions of this type. Questions, deep understanding, flexible question answering is really completely beyond the scope of current AI systems. And let me go back and just point out one thing here. So here's a deep learning system. And here's the input, which is the image, and then here are the output nodes. If you just have 5 output nodes, and each output is one number, then by definition, it's impossible to get complicated question answers out of this system. And there's a saying in artificial intelligence, machine learning, that way predates deep learning, that if you can't represent it, you can't learn it. And this network is not even capable of representing complicated answers to complicated questions. All right. So that's what I think the fundamental limitation is of current AI systems. So now you might say, well, do we need deep understanding? And I think the answer, of course, often is we don't need deep understanding. So in the previous talk, we heard about fascinating, really high-value applications of machine learning, which don't require deep understanding. But you may have seen the headlines recently that seems that progress in self-driving vehicles has slowed down. Well, why has it slowed down? Well, part of the reason, at least, is that final 5% or 1% of autonomous vehicle capability actually does require deep understanding. So here's a good illustration of that. So here's a vehicle, here's a man standing in the road, and what a self-driving vehicle nowadays would do is it would just recognize it as a person, human standing in the road, and then essentially it would just be safe and it would just stop. But it wouldn't be understanding why is this person standing in the road, and is this person just standing in the road, or are they trying to communicate? In fact, this person is trying to communicate with a hand signal. And a hand signal, it's not just a movement of the arm. This is actually language. This is actually an alternative to spoken language. And this symbol means something. This picture is actually from England, so this symbol means something in English culture. In other cultures, it might mean something different. Actually, when I came to the United States, I had a hard time learning that I think this is the symbol for I'm going to turn right. This is not the symbol for I'm going to turn right in England, as far as I know. All right. So to be fully self-driving, a car needs to understand symbolic human gestures. So it really needs to understand language. And so that means that self-driving, autonomous driving, is what AI researchers have for a long time called an AI complete task. And it's not a surprise that many tasks that require intelligence actually simultaneously require many different types of intelligence. And those are the tasks for which we really don't have methods nowadays. All right. What are the consequences of shallow understanding? Well, many applications remain impossible. I had a distinguished colleague at Amazon who was excited about the potential for chatbots, for conversational agents. And he said, well, our software engineers, they really spend a lot of time screening candidates. And so maybe we could develop a chatbot that would screen candidates and save the time of our software engineers. Well, no, I don't think we can. Many applications remain brittle. And so brittleness is the idea that the application really doesn't know what it doesn't know. And it will give an answer even if the context indicates that the question is ill-posed or the answer is completely wrong. There's been a lot of research and public attention to the fact that face recognition systems and other computer vision systems actually are brittle. You can take a photograph of a street sign and in an adversarial way, change just a few pixels in the picture of the street sign. And to a human, it's clearly the same street sign with the same meaning, but the computer vision deep learning system will think it's a completely different street sign. And if you look at even flagship artificial intelligence products like Alexa from Amazon, I keep waiting for Amazon to fix this, but they haven't yet. So you ask Alexa, how high is Mount Everest? You get the correct answer. And then you ask the follow-up question, Alexa, where is it located? And it's not just that Alexa says, I'm sorry, I don't understand the question, or I'm sorry, I can't answer the question. It completely misunderstands the question. I couldn't find that one, but I'm working on adding more local businesses. So essentially it's using templates, and the template, where is something located, refers to the local business knowledge base. And in fact, in academic research and natural language research, this problem is called anaphora. So it is a pronoun, and the natural language understanding question is, when you have a pronoun, what does it refer back to? So here it refers back to Mount Everest. And we do have pretty good algorithms in research for solving the anaphora problem. But making those algorithms robust enough and then combining them with other natural language understanding algorithms to make a production application is a very difficult task. Something also about AI systems is that they actually need excessive quantities of training examples compared to humans. So the self-driving vehicles that are under development nowadays, they are typically using millions of hours of training data. So millions of hours of experience of driving, either driven by a human or under autonomous control and then learning to improve. And if you think about how long it takes a human to learn to drive, well, if you take driver ed in school, maybe you have 10 hours of instruction. But in fact, 10 hours are not enough for a human to learn how to drive, because the typical human in a Western country also has hundreds or thousands of hours of vicarious experience, being driven around as a child by other people. But still, a human learns to drive with at most thousands of hours of experience, and absolutely does not need millions of hours of experience. And it's the deep understanding that allows humans to learn very rapidly. So let's say that you had never been to Boston or New England and you didn't know the colloquial meaning of the word wicked. But then you go to Boston and you hear somebody say it's wicked cold outside, and maybe you hear them use the word again, and you've figured out the meaning of this word very quickly. And the reason is that you have general deep understanding of language. You're bringing to bear everything else that you know. Then this type of, sometimes it's called transfer learning, is really beyond the scope of deep learning or any other machine learning algorithms. All right. So when are current AI methods useful? They're still very useful. The one thing that I'd point out is that from this slide is that many applications, I think most successful applications, are still human-machine partnerships. And often the artificial intelligence actually becomes invisible to the humans. So search engines nowadays have a huge amount of machine learning and natural language processing built into them. But as a user, you don't even really notice that. And finding some information is still a partnership. You type a query, the search engine gives you some results. You look at the results. Based on the results, you revise your query. You issue a new query. And the intelligence actually lies in the combination of the human and the algorithms. I think I'm running out of time a bit, so I'm going to go a bit more quickly. I just want to point out one company that I'm not affiliated with, but which I think is particularly impressive in how they've built an application with high business value, which uses machine learning, natural language processing, but where they have finesse the need for deep understanding. So there's a real shortage of primary care physicians in the United States. And so improving the productivity of primary care is of great business value. And the average primary care visit nowadays lasts about 25 minutes. So if we could reduce the average visit to 10 minutes, then we would have more than doubled the productivity of physicians. And of course, there would be corresponding reduction in expensive healthcare. So how does this company approach the problem? Well, there's an app. The patient describes symptoms in free text, and then the app essentially is using machine learning to map keywords and phrases in the free text from the patient into questions that have been carefully curated as follow-up questions. And then the software asks the follow-up questions, the patient answers the follow-up questions, and then the questions and answers are given to the physician. And the physician reads the questions and answers. And so this essentially short-circuits the first half of a typical primary care visit. And then the physician can ask follow-up questions if needed and have a discussion with the patient, make decisions, medicine, advice, referrals. But it's only the physician that needs deep understanding. And if the questions that were asked by the machine learning system were irrelevant, the physician can just ignore them. And if the physician needs to spend 30 minutes on the visit, then he or she can spend 30 minutes on the visit. So this improves productivity on average. You could call it a chatbot, but that would be misleading, really, because what it is it's a pattern recognition system. It's very similar to that picture that I showed of the deep neural network where the input was an image and then there were 5 output nodes. So here the input is free text from the patient, and then the output essentially is 200 output nodes, just one for each question in the question bank. Should I ask this question as follow-up? All right. Okay, so my title was hype versus reality, or hype versus valuable. AI methods are really useful for analyzing multiple types of data simultaneously. They do have superhuman performance in many ways, in speed, in one very important way in which they're superhuman is in consistency. You can give the same problem, the same question to a human at different times, you'll get different answers. But don't expect genuine artificial intelligence in the foreseeable future. I was at a different meeting yesterday with some machine learning experts, and one thing that we all agreed on is that there are some people that really don't have technical qualifications, but who tweet a lot and who speculate about superintelligence and speculate about killer robots, and but the technology just doesn't exist. There are going to be more breakthroughs in research in the future, and there's no law of nature that says that human-level intelligence is impossible, but it doesn't exist currently. So I think there's actually a very close analogy between speculating about superintelligence and talking about life on other planets. Life on other planets may well exist, and we may well encounter it. And when we do encounter it, then that's going to pose all sorts of interesting, difficult questions. But there's no actual evidence yet that life on other planets does exist. And there's no actual evidence yet that superintelligence is feasible. I get asked the question, are jobs at risk? The answer is yes. But most of the automation that's replacing jobs is not specifically using intelligence. Most of it is replacing physical work and clerical work. And because we don't have methods that can give deep understanding, then we're not going to have any rapid or wholesale replacement of human jobs that require deep understanding. And automation frees up humans for more valuable work. the line I put at the bottom here, the big picture, a great shortage of human labor in teaching and caring. This actually also I got from Jeff Bezos. So I was in a meeting where, somehow normally Jeff Bezos keeps meetings pretty focused, but he does let discussion wander sometimes. And the topic came up of artificial intelligence, and is it going to replace humans? Is it going to destroy jobs? And Jeff Bezos sort of shut down the discussion by pointing out that there's a huge actual shortage of human labor, that any human labor that we can free up from existing jobs, would be great benefit in using it for teaching and using it for nursing and using it for other types of caring professions. And especially if you think about demographics, and which of course is an even more serious issue outside the United States than the United States, artificial intelligence is going to be crucial for helping take care of an aging population. And imagine how much better education would be if there were twice as many teachers for the same number of pupils. And so, jobs are at risk, but they're going to be new jobs, and they may be even more valuable jobs. Okay, thank you. Yes?
So to what degree is the problem of asset management a deep understanding or a deep learning problem? In other words, there's the systematic approach where you have a set of rules that you follow and sort of a fundamental one where you try to take into account a more multifaceted picture. How do you see that evolving? Will it become more automated, you think?
Well, I think there's a lot of continuity between traditional quantitative methods and machine learning methods. If the traditional quantitative methods are using models that are underfitting the data, that are misspecified, and we can have nonlinear models that are better specified, or nonlinear models that take advantage of more data, then I would say those would still be traditional quantitative models. They would just be better, more sophisticated traditional quantitative models. And there is still but the models are not going to have a deep understanding of what they're doing. There's this electric car company out there which has a CEO who's rather a loose cannon. And that's something that a human can understand, and maybe a human can use some judgment to override a quantitative model in the case of this particular company. And it's not that we have data about hundreds of companies with hundreds of CEOs and how they tweet, that we really have enough data to build a quantitative model of CEO tweeting. So I think this is an example of where deep understanding is going to continue to be valuable in combination with the maybe more precise but still shallow quantitative modeling. Yes?
Thanks for the talk. I have a question like regarding the deep understanding pieces. So do you think, for example, in asset management case, so we have different data source, Twitters or whatever alternative data, right?
Yeah.
So, do you think if so we can build some sub models for different perspectives so that we can increase the deep understanding of the model?
Well, I think understanding, it's not binary, either shallow or deep. It's a question of degree. And as we bring in more data, as we bring in more sophisticated methods, we're going to be increasing the quality of the understanding. But I think that foreseeably there's going to still be in room and necessity for a human level of oversight. So people ask me often about alternative data. And one of the really unsolved problems with alternative data is unknown sample selection bias. So, for example, hypothetically, supposing that you got sales data from Walmart every day for Procter & Gamble products versus Unilever products. And so, this might give you some information towards the relative performance of those two companies. But you're just getting the data from Walmart, or you're just getting the data from American Express. And you don't know how Walmart customers are representative of the entire universe of customers. There's a sample selection bias between the Walmart customers and the entire universe of customers. And that sample selection bias is shifting over time. And I think it's going to be up to the humans to have some deeper understanding, which may actually come from conversations with executives at Walmart or executives at Procter & Gamble and Unilever, to figure out how representative the Walmart data is of the phenomenon that you're really interested in general. And if there's one thing that's certain about data analysis methods, is that if you don't have data, the methods can't do anything. And something I didn't say at the beginning, but which I could have spent some time on, is among these different subparts of artificial intelligence, the one where the progress has been the weakest, I would say, is automated reasoning. So in the 1970s and maybe 1980s in particular, there was a lot of excitement around AI systems that were called expert systems. And the idea was that human knowledge would be represented in software and then automated. And expert systems turned out to be, they had a few successes, but they were mostly a failure. And they haven't come back. And so the idea in the 1980s would have been that we'll take somebody who is a successful discretionary portfolio manager, and we'll interview that person, and we'll get all his or her knowledge and heuristics, and we'll put them into software, and then we'll have an automated reasoning discretionary portfolio manager. And that is still, beyond the state of the art. Nobody knows how to represent the knowledge that lets a human have deep understanding.
Excuse me.
Sorry, go ahead. Anton, go ahead.
Can I ask a question?
Yes.
Sorry, is it me?
Anton, go ahead.
All right. So you mentioned some of the recent algorithmic advances that have led to this revolution in deep learning. Can you elaborate a little bit on what's been happening since 2010?
Yeah. So one set of advances has been so-called LSTMs, long short-term memory networks, and they have a particular architecture which solves a problem which is called the problem of vanishing gradients. So essentially, neural networks are trained by optimization using derivatives, but when you move in the direction of the derivative, but if the derivative is zero, then you don't know in which way to move. And when you have a network that has a lot of depth, then the derivatives tend towards zero, or you change the architecture, then the derivatives explode. They tend towards infinity, which also makes the gradient-based optimization fail. And so now we have methods that keep the derivatives bounded, which means that we can do the training for networks which have much greater depth. And if it's a recurrent neural network, or whether it's a deep network, the current networks, even though if they don't look deep in the diagram, when mathematically they are deep also. That's one big set of advances. Another big set of advances is called dropout, which is a new regularization method. So neural networks have millions of parameters, or can have millions of parameters. And actually millions of parameters is not too many when you have billions of data points as input, which you often do in a computer vision application. But you still need to make sure that the neural network doesn't overfit the training data, that it isn't simply memorizing the training data. And in the 1980s, there were essentially two methods invented for reducing overfitting. One's called regularization, the other is called early stopping. And there's a new, really different method, which is called dropout, which is a type of randomization that's pretty similar to what random forests do.
I think we need to wrap up there. We're going to take a break now, and we'll start the panel promptly at 11:10. Thank you, Charles.
Thank you.